So, hello everyone. In this particular video, I'm going to tell you about, I will start the topic recursion. Now, recursion in itself is a very important topic and actually becomes a very important one when it comes to the questions such as of like combination sums, like you have to return the combinations or you have to return the number of combinations which will be equal to some k or subsets, subsequences kind of thing. So, like there is one approach which I've discussed in the bit manipulation topic, that is your brute force one. But other than that, the more optimized way, this is your recursion. And in other words, the method is also known as recursive way. So what is recursion basically? As I will start. So you will find all the things one by one. So what is recursion here? So recursion is simply, in basic words, I just define it, that when a particular function, when a particular function, when a particular function calls itself, when a particular function calls itself till a time, a specific condition, a specific condition, a specific condition is not met. So if I go back to the page and if I just again, or if I just explain you what I've written here. So basically, if you have this question in your mind that what is recursion? So the answer to this question is that when a particular function, when a particular function calls itself again and again, understand this, when a particular function calls itself again and again until a specific condition has met, or it has met until a specific condition is not met. So this is known as recursion, and the function is known as recursive function. And this particular condition, okay, so I have to raise this, and let me just explain it. And this particular condition, and this particular condition is the condition which should be met in order to terminate recursion, is known as your base case. Now, for every function or for every problem, if you want to do it with the help of recursion, then you have to get this base case. Otherwise, just like a for loop, it will actually iterate again and again and again and again. And the other problem, if the base case is absent, remember this. First of all, the loop will run again and again and again. And the other problem, if the base case is not there, then remember this, backtrack or backtracking. Backtracking won't happen. Backtracking will not take place. Now, what is backtracking? How, what is this all about? So, you will understand this later on. So, like, you will understand this, but basically, first of all, just keep this thing in your mind that if the base case is absent in a recursive function or in a recursive method, like, then two things will happen. The very first thing is that particular function recursively will run again, again, and again, and again, again, and again. And secondly, backtrack will not happen. So now the concept of backtracking is more prominently when you do multiple function calls. Like if a function is there which is very simple and for only demonstration of recursion, then you won't find that much of role of backtracking. But if you're doing multiple recursion calls, then if until and unless the first recursive function is over, that is until and unless it has reached the base case, your this particular function, which is for backtracking, it won't happen. So how recursion is takes place? So I will be telling you. So basically, when I explain recursion, I just try to clear it with a very simple example that is of a factorial of a number. What is it? This is a factorial of a number, and factorial of a number you all know is denoted by n and this particular sign, that is your n factorial. As simple as that. Now, if I ask you what is factorial, then in very simple words, it is a continued product sum of that particular number starting from 1 to that particular number. Like if I take, for example, 5 factorial, then your answer to this will be continued product from 1 to that number, that is 1, 2, 3, 4, and 5, which gives you the answer equal to 120. Now, here are two options. If I just tell you that, let me just make you understand this. So, here are two solutions. Like if I just suppose I say you have to solve this problem, like for using for loop or using iteration, you all have must have done. But if I just tell you this particular problem you have to do, and you have to do how? You have to do simply using recursion. So the very first thing when remember this, so the very first thing when you have been given a task to do this particular problem with the help of recursion, then you have to do simply what? You have to simply first identify the base case, because corresponding to base case, you will be able to write your function. So here there are two possibilities of base case. Either you take the base case equal to 1, that is every time you have taken the value and you have passed it. Like suppose if I have taken the value n equal to 5 and I have passed it to the function, and it will recursively like go on till the base case has been reached. And base case here will be when the one function, when the number doesn't become equal to 1, or when it becomes equal to 1, I will simply be returning this particular 1. Or the other condition is that when it becomes equal to 5, I will be simply returning this particular number. As simple as that. But like for this particular case, you will do what? If you have to do till 1 or till 5, then you have to pass the value, like you have to increment it every time because it is a continued product sum. So if I have given the input n equal to 5 and you have passed equal to 1, then how you have to take two variables then in that case? Simple. And you have to take it like when I equal to becomes like that particular number, then you will simply return that particular number, or otherwise you will do the multiplication and you will every time you will increment it or decrement it depending upon the base condition. So how it will be, let me tell you. So in order to first to do the factorial problem, so what we are going to do, I will be trying to explain you like using a very simple code. That is, I will be taking the value here, I will be returning the integer value because factorial is obviously a number, and your function will be fact. This is not the final code. I will be explaining how I'm writing, and I will be passing here an argument that will be the number that you want to get the factorial of. And inside the function, first you have to decide the base case. Suppose for now I have taken the value that when n doesn't equal to becomes, or when it becomes equal to 1, because I have to return the value returned. Like I have to return the value of integer type. So what I can do, I can simply return here 1, because when function becomes, or when the number becomes value equal to becomes 1, like when it becomes equal to 1, then you have to do what? You have to simply return 1. Or you can do what? Because you have to return integer value only, and factorial is the continued product sum. So you can do simply here what? You can take that particular number and you can do this multiplication, and every time for recursion, you want to, because you have to reach 1, your base case is 1. So you have to actually decrement the value by 1 every time. And this will be your. Now, suppose that before I actually code this particular problem, you will find this, like how I will be going to explain. So just see, I passed through the main method, I passed the value equal to 5. This is the case. And then I did what? So your function fact, I am taking fact here by the letter F only to make things simple. So your function will be having initially 5. Now, 5 is not equal to 1, so your base case as of now is not satisfied. So this function will go and this function will do what? If your base condition is not satisfied, then you have to do what? You have to take that number into, you have to decrement it. So your function now becomes 5 asterisk that is multiplied f4. Now this will again run iteratively. So it will again check the condition. So 4 is also not equal to 1. 4 is not equal to 1. So your base case is still not satisfied. So it will come again. So it will do what? 5 into 4 into f of 3. Now it will what? 3 is again not equal to the 1. So base condition is still not met. So I will do what? 5 into 4 into 3 into f of 2. Now f of 2 is what? F of 2, the value of n is equal to 2 is still not equal to 1. So it will be 5 into 4 into 3 into 2 and into, it will simply become f of 1. Now, when the value of n becomes equal to 1, then as per this condition, it will become what? This will simply become like now you can say the value of n has become equal to 1. So the base condition is met. Now, when the base condition is met, what I was supposed to do? I have to return 1. So if I just do it finally, so now base condition has met, that is no more recursion will be taking place. And I can write here simply 5 into 4 into 3 into 2 into 1, which is basically not anything else, but it is equal to 120, which is the required answer, and you can get it through any kind of object calling and function calling. So this was the case of recursion. And now you find that this loop could have go on and on and on if your this condition would not have met, like as simple as that. So this is your base case. This is your base case. Now, in this particular section of recursion, I will also going to like I told you about one thing more of if the not there is no return statement, that is backtracking won't happen. And I also told you that backtracking is more explanatory when you have multiple recursion calls. So I'm also going to explain you about something called as like how you will be getting the concept of return here, like exactly backtracking, how you will get the concept of multiple recursion calls as well in this particular section of recursion. So you will just find it. I will be going on to particular thing called as you must have learned this also. This is called as Fibonacci number. This is called as Fibonacci number or Fibonacci series you call. So I will be writing here series only. So what is Fibonacci series? I will be telling you. So Fibonacci series is like 0, then 1, then comes the value of sum of these two numbers, that is your 1. Then comes the sum of these two values, that is your 2. Then comes the value sum of these two numbers, that is the last two numbers, previous two numbers. What? If you want to find the Fibonacci value at any value, that is any series, like if you want to, these are like first Fibonacci number, second Fibonacci number, third Fibonacci number, and this is your fourth Fibonacci number. Now, if I simply say that you have to want to find the fifth Fibonacci number, so fifth Fibonacci number is the sum is equal to the sum of the previous two elements of the Fibonacci series. So this is 2 and 1, so this will become 3. Then it will become 5. Then it will become 8. Then it will become 13 and then 21 and then so on. So this is basically what this is your Fibonacci series. And if I just suppose ask you that you need to find out the fourth element of the Fibonacci number. So in order to do this, you can do it with the help of for loop, and you must have done it also. Suppose if I ask to you to find out the value of the fourth Fibonacci number, that is fourth element of the series. So the answer should be f of 2. Like the answer should be 2 here. So how you will going to do it? And if you do it with the help of recursion, then this particular type of concept will take your multiple recursion calls. Like I will writing here, this concept will be taking your multiple recursion, recursion calls. As simple as that. Order to get, suppose I need to get here the fourth element. Like what? I need to get here the fourth element and of this particular Fibonacci series, and the answer should be 2. Now, in order to get the, as I told you that in a Fibonacci series, if you want to get the element, the at nth element, then you have to get the value of the previous two elements. And in order to get the value of those previous two elements, you need to get the value of respectively those two previous elements of that particular number. Now, suppose if I need to get the value of f4, Fibonacci 4, then it will be simply the sum of f3 plus f2. And you also know that f3 will be the sum of f2 plus f1, and f2 will be the sum of f0 plus f1. As simple as. So you have to find that the like zeros is not any index. So if you just calculate it here, so you will find that zero is not the index. So indexing starts here. Fibonacci series. It's not a string, it's not an array. So your particular string will start from one. So you can only take it till one. As simple as that. So you know this. So what will be our base case if you want to calculate any value? Like till what particular index that it can reach, and like for which till which element? Like here 4 stands for your the particular element that you want to find of the Fibonacci series. So starting element of the Fibonacci series is the first element. So obviously your n will, or anytime your n can only go to the value 1. So this obviously becomes your base case. This obviously becomes your base case. Now, how you will be executing here? So, what I did here is basically your recursion tree, and you can simply make it also in the form of a recursion tree as well for factorial. And for exactly like this is the dry run as well as your recursion tree as well. Tree can be made in the form of a tree structure, and recursion tree is not the binary or any kind of tree that you must have heard of. So, how is it made in case of Fibonacci? So let us see. Suppose I had to find out the fourth element of the Fibonacci series. Then firstly, I will be passing n equal to 4 because I need to take out the fourth element. Then I will be doing here what? I will simply be trying to take here the value, as simple as that. Just see. I will simply be trying to find out the value here. Fibonacci will be equal to f of 3 plus f of 2. Like any particular nth element in Fibonacci series is equal to the sum of n minus 1th element plus n minus 2 element. As simple as that. And f of 3 will be equal to f of 2 and f of 1. And f of 1 will simply be equal to here. As simple as that. F of 1, because there is no 0th element. And f of 1 will remain f of 1 only. Same goes for here. F of 2 will remain here f of 1. So the base case was till the time the indexing can't is equal to 1. As soon as it becomes equal to 1, your base case is satisfied. This is what I discussed here. that this is your base case because the nth lower limit, that is the starting value of a Fibonacci series, that particular place is your first element. So obviously the value of n can't go below 1. So when it reaches 1, now here you see every time there are two functions here. For f4, f3 is there, f2 is there. So that means there will not be one recursion call, but there will be two recursion calls. So this is actually a multiple recursion call system. You find it for F4 we have to calculate F3 and F2. For F3 we have been calculating F2 and F1. So just like that. So I told you if you don't have the return statement, then your function won't backtrack. And this is to clearly inform you that when we are making a binary tree here, this is what? This is not a binary tree here, but this is a recursion tree. This is what? This is a recursion. This is your recursion tree, as simple as that. So this is your recursion tree. Now you have to do here what? Let me tell you. So if you find here that this particular case, if you don't had, sorry, if you didn't had like your return statement, then this particular function won't backtrack. Now, what I say by backtracking is that when you make a recursion tree, you should always keep this thing in your mind that first left part of the recursion tree is executed. First left part of the recursion tree is executed. Like now, I explain you what I meant to say. When you made F4, then F4 is always can be done by F3 and F2, and F3 will be done by F2 and F1. So firstly for F4, F3 will be executed, and when you come to F3, F2 will be executed. Then for F2, F1 will be executed. Just like that. You reach the n is equal to 1, your base case arrived, you saw the word return, then you will do here what? You will backtrack. This is backtracking. You backtrack, you go to F2, and F2 never had anything the other than that. So F2 will also come here. Then you will come to this particular place, F1. This will be having its value, and you reach F3. So now F3 recursion call is over. Then you again backtrack to F4. So you reached F4. Then you had F2, and F2 again left half will be executed. So for F2, F1 can only be there because there is nothing like zero as element in Fibonacci series. So F1 is reached again back, like you met the base condition, so you will again backtrack, and there is no point because your recursion is over. So every time you are backtracking, this is particularly returning its value. As simple as that. This is particularly doing what? This is particularly returning its value. So you just need to remember that when you are making a recursion tree, first the left half of the tree is executed, and then you backtrack, and then again you go. So this concept is important, and multiple recursion calls you will be also using in different problems like rat in a maze and queen kind of problems. So you will be using it. So, so I just told you one thing that when the base condition will be reached, then these functions will not just only backtrack, but while backtracking, they will also be giving their values. They will also be returning their values. They won't return alone, they will be returning with their value. Like F1 you will read, then the value of F1 as per the Fibonacci series is simply 1. So this will be sending you 1, and here it will be 0. So obviously this will be 0. And then here what? Then you will be finding here the value F3. So F3 is what? This particular function has got 1, and this particular function, then you will be reaching here control. And this particular function will be backtracking, and this will be giving you 1. So you will be reaching here where you this one and this one will become 2 for you. As simple as that. Then you will be reaching here with the help of backtracking, and then you will reach here F2. So F2 is what? It is simply 1, I believe. Your second element, if you go by Fibonacci series, then your first element is 0. Remember this, first element is 0, and then your second element is 1, your third element is 1. So I just think I made a mistake here. So this is 1. So this is obviously 0 here because your first element is 0. Then there is nothing here, so this will be returning 0. and you will be doing what? So you will be keep coming here. This will be returning you 0. So you just went here, and then you went here. So this becomes F3. F3 will reach this particular place, and this will do what? This will simply take you to, by backtracking, this will do now come to the right half, and this will reach to F2. And F2 will be doing what? F2 will be recursively coming here. So this will be coming 1, and like this will be coming 1, and this will be coming what? Here is nothing. So 1 is 0. But when you will coming back to 2 again, when you will return, so this 2 has its value equal to 1, and this 3 has its value equal to 1. So like you will finding this 1 and 1, when they will return here, they will simply give you the value equal to 2. This is the fact. F3, because just remember this, when the functions are being backtracked here, remember this, I told you, when the functions are being backtracked here, they are not just returning alone, they are returning with their values. So this is the case. And for F4, this one and this one will become equal to 2. As simple as that. So you can check the answer. If you write 4, you will be getting equal to 2. So basically, if you try to find out the indexing of this Fibonacci series, then this particular index is assumed to be 0. So if this particular index is assumed to be 0, then your fourth, like there is a slight correction here that your fourth index comes at 3. As simple as that. So fourth index comes at 3. So now in that particular case, your recursion tree will be having its value f1 and f0. As simple as that. And f1 will simply be having its value f0. Again f2. So f2 will be having its value f1 and f0. So now f1 will be having its value 1, and f0 will be returning its value 0. So the reason was that here that this particular function will be backtracking, and it will be returning here the value. The reason that it was not being mentioned by me in the binary or in the recursion tree, sorry, in the recursion tree, the reason because which it was not being mentioned by me in the recursion tree was that this particular function, when it will be backtracked, it will simply be returning its value that is equal to 0. And same goes for here. But ideally, when you should get the answer, so you should be getting the answer f4 is equal to 3. So there was a this was a slight correction that even you have to mention it in the recursion tree, so that makes it a bit more clear. You can't just skip it because it will backtrack the value less than equal to 0. Now you will be finding it how will the function, how the base condition will change. It won't change as such. It will still remain something equal to 1, but it will change like this, that 0 will be having its value 0. So when it will be backtracked, still you see, if you just write the value 0, so that will have its effect. Like indexing will change. Remember this, your indexing will change. As simple as that. This you have to remember here, that your indexing will change, that like that it will start from 0. From which index it will be starting? It will be starting from 0. Understand this. You can't just simply skip that particular index. What I initially just explained you, I tried to skip that particular f0 value because f0 will be returning you on backtracking the value 0. But you shouldn't skip it. Like I stand corrected here that seriously that you shouldn't skip it, and because that will result your f4 equal to 2, but actually its value is equal to 3. So now your base case becomes equal to, since on backtracking f0 will return value equal to 0, so it becomes less than equal to 1. That as soon as your term value becomes equal to 1, that means simply you have to backtrack and you have to return it. And therefore, your Fibonacci series, this particular number, when you include it in the recursion tree, just understand this. I was not including in the recursion tree, so I was getting this particular, like my fourth element, this one. But actually, the fourth element is the third. Like, is the value is equal to 3. So when you include it in the recursion tree, you will be finding it like the value will be equal to the value will be equal to 3. Now, in before I just move on, I just would like to tell you about the time complexity of this particular program. So, on seeing the recursion tree, you will be finding that for each and every function call, there are two. There are what? There are two. So, as simple as that. If you just see here, if you just simply see, as simple as that, as simple as that. What you find here? F4, you had two calls. F3, you had two calls. F2, you had two calls. So, for like here, the time complexity would be in exponential form. Like for n, like if you point for the nth term, like Fn, then your time complexity would be reaching here somewhere close to 2 to the power n. That is your exponential time complexity. And if you want to find how many, what is the like space complexity? So here, space complexity is determined by the term called as stack space. What it is called? It is called as stack space. So stack space is basically determined by the number of function calls in waiting. Here I have just have to erase it. Before being. So again I am saying that if you will include the number f0 in the recursion tree, I was not including the value f0. The reason being was that it returns the value 0 on backtracking. So you include it because if you don't include it, then you will simply get the value f4 equal to 2, which is actually wrong because the fourth element of the Fibonacci series is 3. That is the next element. So you have to include. Don't just simply leave it because when you don't include, then your program actually gets you the value equal to 2. But actually, you should include it. Don't just leave it because it actually, returns the value 0. This is the correction. So I was telling you about the stack space. That is your space complexity. So stack space is simply the number of recursion calls or the number of function calls, that is simply the number of recursion calls because the function here is recursive, are in waiting before being backtracked. So you just understand the meaning here. Like before being backtracked here, how many calls were there? This is your first call, this is your second call, this is your third call, this is your fourth call, isn't it? And the n value was equal to 4. Understand this. This was your first recursion call. This was your second recursion call. This was your third recursion call, and this was your fourth recursion call. So when it will be backtracked, the number of recursion calls that were in waiting were simply equal to n. So the time complexity would be, or sorry, the space complexity that is determined by the state space when you have to find the fn value. Like here it was f4. In that particular thing, when you have to find fn value, then your space complexity would become big O of n. And I must have mentioned about the time complexity. So your time complexity here is exponential, that is 2 to the power n. So wherever you find this kind of data structure, like in a form of like first that is F4, then it is coming to F3, then it is being subdivided, and here from F4 it was being subdivided kind of thing. So you have to remember that its time complexity would be exponential. And the other thing is that in your recursion tree, always try to include this particular value, that is your F0. I know that on backtracking, it will return the value equal to 0. But if you don't do it, then your recursion will give you the answer f equal to 2. Therefore, I just corrected myself and just told you the thing. Okay. So now all this is done. And if I tell you the time complexity of your factorial program, so its time complexity would be simply big O of n, and its and it's stack space, as simple as that. So its stack space is simply equal to its stack space is simply equal to big O of n as well. As simple as that. Your time complexity here is what? Your time complexity simply you have to do here what is that your stack space is here is equal to number of recursion calls that are in waiting is simply equal to n, and so your time complexity is equal to big O of n. So now we will move to the coding part and just show you the output. So I will be creating here a file called as recursion.cpp, and I will be doing here what? I will simply be doing here as include stdio or like bits tdc plus plus h, and here simply int main, or I will be creating here a function that will be int fact, that will be taking an integer value, and I will be doing here what? I will be mentioning here something in if, and not exactly this. What happened? So what will be the condition I told you? If the given number on decrement by 1 becomes equal to 1, then you are returning an integer value, so you have to return your 1. Otherwise, you will be returning your. Remember, as soon as one return is identified or one return is encountered by the function, it simply returns it. So you will be, because it is a continuous product sum, so now you will be recursively calling it how? You will be simply decrementing it. So this is your function. And now how you will be doing it? I will be calling here an int main, and I will be passing here an int n equal to 5, and then I will be simply like passing here the out factorial of a number that is simply equal to fact n, and I will be passing it in quotes. So this is your quote, and like this shouldn't, colon shouldn't come here, colon should come here. Now this will run. So I'm just checking the output, and you will be getting the answer equal to 120 that we calculated through the concept. So let's see. You got the answer here. Just check this. If I just tell you, you got the answer, see this factorial of a number equal to 120, you gave the input equal to 5. And next we will be seeing the code for the Fibonacci one as well. So what we have to again return the value equal to an integer value only. So Fibonacci, and you have to give the term. So, and here because we have to go till 0, remember this is a big case, and I will be mentioning in the comment also because I also made the mistake, because we have to recursively call or recursively call till n equals to 0. This, remember this, and then it will simply return while being backtracked. It not only backtracks will happen, backtracking will be happening with the help of return keyword, and it is also returning the value. So it will be returning the value, and here it will be doing what? Just remember this. It will be simply doing Fibonacci, oh God, Fibonacci. It will be doing n minus 1 plus Fibonacci n minus 2. This is the case. As simple as that. I hope it's clear. And then Fibonacci term. You will be finding here, I will be mentioning here Fibonacci. And here, instead of 5, I have to check for 4. So now you will be finding how we are doing. Now, if you just return how I'm returning this, so for a Fibonacci term, if we want to take out a particular term from that series, one term is actually equal to the sum of the previous two terms. So this is the case. I will be running this code and you will be finding here the particular term. So Fibonacci term equal to 3. And fourth term of a Fibonacci series, as I told you, just see this. Fibonacci term of a given series, like Fibonacci series, if you want to find out, it is 3. And initially, if you don't take it less than equal to 1, just suppose, if I just take it for equal to 1, you will be finding this, that this will be returning f equal to 2. Just find this. Actually, it is not returning the value because what will happen, just let me tell you, it will never reach that particular condition. As simple as that. The reason is what? It will never reach that particular condition. So ideally, you have to go till 0. That is a particular case because otherwise you won't reach that particular thing. The reason is that therefore, if you don't traverse, if you have to, if you won't be traversing through till 0, then what you will be getting here is that you will be getting your value equal to 2 other than equal to 3. The ideal value is the fourth term of the Fibonacci series is 3. That's what you are getting here. And like it is the third term, sorry, it is the fourth term which is equal to 3. And the reason was that if we are not traversing till f is equal to 0, then it will simply give this error. So though on backtracking it will return the value 0, but it has to be included. And when I was not including the value f equal to 0, therefore it was coming till 2. And therefore, if you're not including it, then you will start indexing from f equal to 1, obviously. So your first term will become 0 and so on and on and on. So it won't return. So ideally, you should traverse starting from 0. That is the 0th index. Remember this. We have not recursively called, but if we have to traverse till n equal to 0, I will be mentioning here, and I will also be mentioning this particular thing, starting index, because you can also make the mistake. So this was all about your recursion first part, and I will be creating one more video on the concept, which will be having some better questions and which will actually be having multiple recursion calls, and they will make you understand the concepts better. So thanks for watching this particular video, and do remember this particular concept, which actually I also made a mistake here. So you have to keep in mind and practice it. So thanks for watching, and do like, share, and subscribe. Thanks everyone for watching.